Hi, this is Physics 503, Nuclear Physics, and we're still on our lesson on the overview of nuclear reactors and research reactor technology. In the second part of this lesson, we're going to discuss the general components of your nuclear power reactor and the different types of your nuclear power reactor.
In the previous video, we'll discuss about the main drivers of your nuclear energy, which are the following. You have a high power density, you have supply reliability, economics and increasing fuel cost. We've also discussed about the carbon emission cost and the operation history and safety of your different types of energy plants. We've also discussed some of the main issues that we are facing in our country, especially in taking considerations in building our own nuclear power plant. And these are your public acceptance. In the Philippines, we have this low acceptance to the public and also high capital cost. It will take us around 200 pesos to construct our own nuclear power plant. Another issue is on the nuclear waste and the long timeline to start your first nuclear power plant, which will take us around 10 years for just a developing country like us. In this video, we're going to discuss the general components of your nuclear power reactor, the core, which is comprised of your moderator, your fuel, and your coolant, and then the control rods, the reflector, the reactor vessel, and then the steam supply system. These are the main components of your nuclear reactor. At the center, you have your core, which is comprised of your fuel, your control rods, your moderator, and then your coolant. And then you also have your pressure vessel, and then a steel line reinforced concrete containment, which protects your core from your environment. Let's discuss these components one by one. The first major component is your reactor core. In nuclear energy production, a steady-state chain reaction needs to be maintained. That is, it does not grow or decay with time. So a chain reaction such as this one should be maintained, and it's usually done inside a reactor core. The state of a fission chain reaction is described by the effective multiplication factor K, where K is equal to the number of fissions in one generation divided by the number of fissions in preceding generation. A reactor that is critical, that is when K is equal to 1, means that it is neither gaining or losing free neutrons in the core. And this is what we want with our reactor, a critical reactor. So this is what is inside of your reactor core. So you have your fuel rods and then your fuel pellet. And you have here your control rods and then your moderator. And inside your fuel rod happens or your fission reaction takes place, and then it is moderated so that it can uh, the the neutrons that were released in the previous fission can be absorbed by uh, other nucleus in other fuel rods. And you have here your control rods, which you can move up or down, and this controls the reaction inside your reactor core. We're going to discuss more about your control rods in the next slides. Your typical fuel materials are your uranium, typically enriched around less than 7.7% of your uranium-235, and you also have your natural uranium-238, and you have your plutonium-239 and 241, and also thorium-232 in some research reactors. So your fuel rod is composed of many fuel pellets, and these are arranged in a cladding. Your cladding is usually made up of zirconium, which is transparent to absorption and also to dispersion. And it does not interact with with the fission reaction. So if you're going to use a zirconium in your cladding, the we can always maintain your the criticality of your reactor. So this is now your fuel assembly, an assembly of many fuel rods. And for your typical or your most widely used power reactors, like say for example a BWR or a boiling water reactor, the fuel assembly may be about 320 kilograms with 183 kilograms of uranium. And for a PWR or a pressurized water reactor, can be around 655 kilograms with 460 kilograms of uranium respectively. The material in the core which slows down the neutrons released from fission so that they can cause more fission is what you call your moderator. Again, the purpose of your moderator is to slow down the neutrons released from fission so that they cause more fission. So typically when you start or when you start your fission process and then you produce more neutrons, there are at least three types of neutrons that can be produced. You have your thermal neutrons, your epithermal neutrons, and then your fast neutrons. As you can see from this graph here, the probability of, fission to occur for fast neutrons is very low. Also for your epithermal neutrons. So what we want is that your neutrons should be maintained in this thermal state. That's why we stated earlier that fission can fission can occur more if you have your thermal neutrons. And with the help of the moderator, which slows down these epithermal and fast neutrons released from fission, your thermal neutrons can create more fission products in our in our fission reaction. Most moderators used are just your water, average water, and then your 2O, and then your carbon. Okay. And the next is you have your coolant. A coolant is just a fluid circulating through the core. So as you transfer heat from it, it removes heat from the core and other parts of the reactor where heat may be produced. And it also moves or circulates your water or uh, your heat so as to produce the steam that we need to drive your turbine. And your coolant is just typically water and heavy water. That's why you can see most of your power reactors constructed near seas or in any body of water. So that's your coolant. So this is this is the typical circulation of your coolant. So your coolant comes in from one side and then circulates around, carrying the heat, uh, and then the heat is taken outside to produce the steam in the next area here. So the heat is used to boil the water, producing the steam, and then the steam will drive your turbine, also moving your generator, creating now your electrical energy. Next is you have your control rods. Your control rods are neutron absorbing material used to control or halt the rate of the reaction in the reactor. Your control rods are used in the startup and then the shutdown, and also to change the power output or to keep at steady state. So sometimes when there are, like say for example, natural calamities like earthquakes, we uh, we use your control rods to stop the fission reaction or to slow down the fission reactor. So typical control rods used are your cadmium, hafnium, and boron. So if you're going to insert your control rods in your moderator, so there will be lesser uh, fission reactions that will happen because these are blocked by your control rods. And if you want to increase the reaction rate, you just take out your control rods. The next component is your reflector. So this is a thick and filled region of the moderator. Some of the neutrons from the reaction process can actually escape uh, inside your vessel, inside your reaction core. And this reflector will reflect back or will reflect back your neutrons into your reaction core. It diffuses back to the core some of the neutrons that leaks out of the core and improves the neutron economy, the neutron savings resulting to reduce amount of fuel and size of the system. So it helps to maintain the criticality of your reactor. So these are some of the high neutron reflector materials. You have your Be2C and then your ZR3 Si2 reflectors. So this is inside your nuclear reactor, and this is already filled with your moderator, okay, which is just typically again some water. And here, these are your fuel assembly. These are your control rods, and then your fuel assembly, and then you have here around your reflector materials. The next part is your reactor pressure vessel. This is a steel vessel containing the reactor core, the moderator or coolant, and then the generated steam. This is designed to contain nuclear fuel and internal structures and withstand the very high pressure, temperature, and neutron irradiation generated during a nuclear reactor. Sometimes in a nuclear reactor, when your materials are not compatible with your fission reaction, the material will become brittle, which can cause problems later. So the reactor pressure vessel is one that is designed or made or constructed for many years, just to make sure that it can withstand the very high pressure, temperature, and neutron irradiation. It is usually 4 to 8 inches thick. It's heat-resistant steel, namely your MnMO nickel steels. These are some parts of your reactor pressure vessel. So these are some images of your reactor pressure vessel. So this one here, you usually make your or construct your reactor pressure vessel for at least 3 years. So when you're going to plan to make or to construct a nuclear reactor, you should order first your reactor pressure vessel uh, first before doing other activities, because this will take more time as compared to constructing the plant itself. Again, your reactor pressure vessel contains your core, your moderator, your coolant, and so on. Then we have your steam supply system. So this is just how your your steam flows around. So you have here your steam generator number 2. So you have here your nuclear reactor. So the heat produced from this one will be used to boil this water, and then you have steam that is produced. The steam will then be used uh, to move your turbine, and then also and as your turbine moves, your generator also moves, creating your your electrical energy. Your steam supply system is usually used by your LWR or your light water reactors. Your light water is used as a moderator, coolant, and reflector. It is operated at high vapor pressure due to the high vapor pressure of water. So basically, you have two common types of your reactors. You have your pressurized water reactor, or your PWR, and your boiling water reactor. As you can see here, in your boiling water reactor, you do not actually have a steam generator. So what happens here is that you have here your core, and then your moderator, and then also you have here your coolant. So everything that's there, the steam is directly produced in your reactor vessel, and it directly moves towards your turbine. So there is possibility that some of this steam that goes out here can be actually radioactive. Compare it with your pressurized water reactor, where you have a separate steam generator. As you can see, the reactor vessel is not directly connected to your steam generator. There's just some line here where your heat travels, and The heat here will then be used to boil the water to generate the steam. So there is no direct interaction with your your water or your moderator or your water with your reactor vessel. So your pressurized water reactor is fueled by your uranium oxide clad in zircaloy and maintained at high pressure at 16 megapascals so that it does not boil at the operating temperature of the reactor. Your boiling water, on the other hand, is fueled also by uranium oxide clad in zircaloy, which is boiled water boils in the core to produce steam that directly drives the turbines. Comparing your boiling water reactor with your uh, pressurized water reactor, your comparing the pressure, your PWR is maintained at higher pressure and also at higher uh, RPB temperature. Your PWR has steam generator, and the control rods is inserted from the top of the core, while your BWR, the control rods, is inserted from the bottom of the core. Some of the advantages for your BWR: lower nuclear fuel temperature, lesser components, and possibility to operate at lower core power density levels with natural circulation, and do not use boric acid to control fission borne up. Less possibility of corrosion in RPB and piping. The advantages in your PWR are the following. You have higher power density, hence smaller RPB. Water in turbine is not contaminated. Water in primary loops separately from the secondary loop, and lesser shielding required. The problem with your PWR is that water can be contaminated with your radioactive materials because it is directly in contact with your reactor core. So this is your steam supply system. You have different parts there. You have your steam generator, which transfers energy in the form of heat from the primary loop to the secondary loop to create steam to drive the turbine. And then you have your pressurizer, the component in the reactor coolant system, which provides a means of controlling the system pressure. And then the reactor coolant pump, which is designed to move the coolant through the primary loop so that the heat generated in the core can be transferred to the steam generator. So these are the parts of your steam supply system. You have your pressurizer, your steam generator, reactor coolant, your reactor coolant piping, and then your reactor vessel. The next component is your containment. This is made of reinforced concrete and steel enclosing the nuclear reactor from the environment and to confine fission products in case of an emergency. So these are your typical containment. Okay, where inside of this is your nuclear reactor. Those are your components of your nuclear reactor. Now let's discuss the types of your nuclear power reactors. So we have five types. We have your LWR, your HWR, your GCR, your FNR, and then your newer reactors. Let's discuss this one by one. These are your classification and characteristics of your different types of your nuclear power reactors. We have in terms of neutron flux spectrum, you have your thermal neutron and then your fast neutrons. So for your thermal, you have your light water, heavy water, and then your graphite. And then for your fast, we don't have a moderator. For your thermal, you can use coolants such as light water, heavy water, and gas CO2. And for your fast, you can use your liquid metal and the fuel materials usually for um, light water are enriched uranium. For heavy water, natural uranium. And for your graphite, you can have your natural or enriched uranium. And for your fast, you can use your plutonium and thorium. These are the reactor types. For your PWR, the fuel is enriched uranium. The coolant is water, moderator is water. For your boiling water, the fuel is enriched uranium. The coolant is water, moderator is water. For pressurized heavy water or heavy water reactor or the CANDU, it uses natural uranium. The coolant and moderator are heavy water. For gas-cooled reactors, you can use natural uranium. and then enriched uranium. The coolant is CO2, and then the moderator is graphite. For your light water graphite reactor, you can use enriched uranium as a fuel, and then water. For coolant and moderator, you have graphite. And for your fast Newton reactor, you have your uh, PuO2 and then your uh, UO2, and then your coolant is your liquid sodium, and then moderator, uh, you don't require a moderator for your FBR. These are some of the operable power reactors according to types. So as you can see, mostly your power reactors are boiling water reactors, especially around Asia and North America. So most of the operable reactors are boiling water reactors here. And for your pressurized water reactor, it tops the list. 92 plus 2 around Asia and also in East Europe and Russia. 102 in West um, Central Europe. So many of the reactors that are operable are usually boiling water reactor and your PWR or your pressurized water reactor. The first type of reactor that we are going to discuss is your pressurized water reactor or your PWR. This is the most common type with about 300 operable reactors for power generation and several hundred for naval propulsion. It uses ordinary water as both coolant and moderator, and consists of primary cooling circuit, which flows through the core of the reactor under very high pressure, and a secondary circuit in which steam is generated to drive the turbine. Again, in your pressurized water reactor, the reactor core and then uh, your your steam generator is separated, unlike your boiling water reactor. Fuel is slightly enriched uranium, around 2 to 5%. This is a schematic diagram of your PWR nuclear power plant. Your pressurized water reactors were developed by Westinghouse for power source of nuclear submarine, now TDUS, in 1955, and later commercially at the shipping port in PS Unit 1 with 600 megawatt electric of energy in 1957. Again, the primary coolant is light water, and the primary coolant of the system is radioactive. The moderator is light water also. You have your the water steam cycle pressure at 16 megapascals. The secondary coolant system is, however, not radioactive, so there's no problem here with the steam going out because it's not anymore radioactive. These are some of the common PWRs in the world. You have your Yankee and then your Korean nuclear power plant in South Korea. We also have your Sanmen nuclear power plant in China, which is the newer one. The next type of your reactor is your boiling water reactor. This is just similar with PWR except that water boils in the core and steam is formed in the reactor itself and goes directly to the turbines where you have a direct cycle. And as you can see, since your water boils inside the core, water actually becomes radioactive. It has higher heat efficiency, resulting to lesser water to be pumped versus your PWR, and operates at pressure at about half of that of your PWR. Your fuel is slightly enriched uranium, around 2 to 5%. The General Electric aimed at following Westinghouse and designed the BWR based on different concepts. First commercial BWR is Dresden Nuclear Power System Unit 1 with 180 megawatts electric in 1960 at US. So you just have a single loop which allows water to boil in the core. Your coolant is light water, your moderator is light water, your steam cycle pressure is just at 7 megapascals. Boils at the core at 285 degrees Celsius. A mixture of steam and water leaves the RPD. The coolant is boiled uh, in an RPB and is directly sent to the turbine, thus making your water here radioactive. Some of the boiling water reactors around the world is your Limerick nuclear power plant, and then your Dresden one, which I think is already decommissioned. A very famous nuclear reactor, a boiling water reactor, is your Fukushima Daiichi nuclear power plant. Daiichi meaning one, so it's the first nuclear power plant in Fukushima. So it's famous because, of course, this is the nuclear reactor which had an incident just recently because of the earthquake and then the tsunami that happened in Japan. And it has around 4 reactors, which can produce up to 1,100 megawatts electric. We'll be discussing more about the Fukushima incident in the later parts of this course. So it's a boiling water reactor. So as you can see, it's also near the sea because it uses your light water as coolant and moderator. The next type of your nuclear power reactor is a light water graphite reactor, known as your LWGR, or most commonly known as your RBMK. The RBMK stands for Reactor Bolshoi Nosky Kanalini, which stands for your high power channel type reactor. This is a class of graphite moderated nuclear power reactor designed and built by the Soviet Union. So your reactor Bolshoi Moshnosky Kanalin RBMK. So it's really known as your RBMK in Russia. The coolant is water. It employs long vertical pressure tubes running through your graphite moderator. No RPB containment and only shielding. Fuel is low enriched uranium oxide made into fuel assemblies, 3.5 meters long. So one example of your RMBK is your Chernobyl power plant, which I believe you also know about. So there was this incident in 1986, the Chernobyl incident, which also prompted the Bataan nuclear power plant to not be commissioned. So because of this accident here. So this is a power plant in Ukraine, an RMBK, and we're going to discuss more also about the Chernobyl accident in the later parts of this course, along with your Fukushima accident. The next type is your pressurized heavy water reactor, where your fuel is just natural uranium, and more properly known as your CANDU, meaning your Canada deuterium uranium. The coolant is and moderator is heavy water, your D2O, but kept separate, and then it relatively has a larger core than your PWR and BWR because your heavy water is not as effective as your light water as a moderator. It utilizes pressure tubes consisting of horizontal cylindrical tanks or the Candelaria. And below is the process of how uh, your fission in your pressurized heavy water takes place. So this is a fuel assembly in your pressurized heavy water. The mass of a fuel is about 97,000 kilograms. That's very heavy. And there are about 48 in operation in the world for your PHWR. Examples of your PHWR is your Darlington Nuclear Generating Station at Canada, and then your Tinshan Phase 3 nuclear power plant in China. And again, as you can see here, interestingly, your nuclear power plants are constructed near bodies of water, like say for example, in the seaside. Then we also have this gas-cooled reactor. This is an advanced gas-cooled reactor, or your AGCR, a high-temperature gas-cooled reactor. It uses graphite as moderator. The coolant is carbon dioxide and helium for your HTGCR. The fuel for your AGCR is lightly enriched uranium oxide clad in stainless steel, and for HTGCR, fully enriched 93% uranium mixed with thorium. The gases are not a strong absorber of thermal neutrons and does not become very radioactive. The coolant can be heated to higher temperatures than water. As a result, higher plant efficiency of around 40% or more compared to water-cooled designs. An example of this one is your Hisham nuclear power station in the United Kingdom. And we also have your fast neutron reactor, which utilizes fast neutrons, new moderator, to fission your plutonium-239. And the neutron produced are absorbed by uranium-238, which blankets the core, further breeding your plutonium-239. Fast neutron reactor designed to breed fuel by producing more fissile materials than it consumes, and this is considered to address the fuel needs for 1,000 of years, your fast neutron reactors. We have 4 types currently being developed, your liquid metal cooled FBR, you also have your gas cooled FBR, your molten salt breeder reactor, and then your light water breeder reactor. It's still not used, but in the near future, we can see more of these FNR to be constructed around the world. Let's talk about your liquid metal cooled FBR. It uses sodium as a coolant and graphite as moderator. Sodium melts at 880 degrees. It is first melted by electric heating before it is circulated in the pump. Your sodium need not be pressurized, and higher temperatures can be achieved, resulting to higher thermal efficiency and smaller reactors. But sodium reacts heavily with water and becomes slightly radioactive, and it will need more shielding and leak-proof system needed if you wanted to use your liquid metal cooled FBR. Some of the examples of your FNR are your Joyo nuclear reactor in Japan and then your BN600 reactor in Russia. Then you have your newer reactors, your floating nuclear power plants, which can produce up to 70 to 600 megawatts electric. And these are mounted in pairs on a large barge, which will be permanently moored in for electricity generation and also possibly some desalination icebreakers. Electricity loss or electricity cost is expected to be much lower than from present alternatives. What you have here is a Russian TLTS-4S used in icebreakers, a floating nuclear power plant which produces 35 megawatts electric, as well as 35 megawatts of heat for desalination or district heating. And this is expected to run for 3 to 4 years between refueling and will be operated in pairs. The last type of your nuclear power reactors are your small modular reactors, which are still newer compared to the other reactors. Your small modular reactors are nuclear reactors that can generally produce up to 300 megawatts electric or less energy, and this is designed with modular technology using module factory fabrication. Your SMRs may be built independently or as modules in larger complex, which or with capacity added incrementally as required. These are simpler, has smaller, shorter construction times, and lower seating costs compared to other reactors. And this may be a reactor that the Philippines can uh, consider. These are some of the small reactors operating around the world. You have your CNP, your PHWR, and then your GP, your KLT, and then your RITM in Russia, and some small reactor designs under construction in Argentina, China, and also another one in China. So those are your types of reactors, and those are your components of your power reactors.